Hi everybody, welcome to another video in Calculus 1, section 4.6, Linear Approximation and Differentials. So in this section, we learned about linear approximation, and this is exactly just like the equation of a tangent line. So we call the equation of a tangent line, I will write in this form. Y minus f of a equal to the derivative or the slope of the tangent line x minus a. I just need to add f of a to the other side, and then the derivative of the slope of the tangent line will be the derivative at that point. So this is the equation of a tangent line. So what we do now, we use the equation of a tangent line to approximate the values of the function. So let's say we have the function y equal to f of x, and we have a tangent line. Then at that point, the values a, we have f of a, so at that point there's the point of tangency. Now close to that point, the values of the function is here, the values of the equation of the line is here. The further away from it, the less accurate it is, this approximation. So what we try to do here, because we use the equation of a tangent line to approximate the values of the function, the equation of the line is a lot easier to evaluate than the function, right? So in that case, the values, we use these values on the line to estimate these values of the actual function on the curve. Of course, this approximation only works if it is close to the point of tangency. If it is too far away, this approximation is not very good. Right. So once again, will be in this form. This is the equation of a tangent line, and we use f of x equal to that, just an approximation using the line to estimate the values of the function. Right. Now with that, what do we use? How do we use linear approximation to approximate something like this, square root of 8.85? So before we do anything, so let's just write out the equation or the linear approximation. F of x approximately equal to the values of the function at a plus derivative at a x minus 8. So we're going to use that formula for linear approximation, which is of course the equation of the tangent line. Now we just need to identify what's x, what's a, and what is f of x. Of course, when we have the function, we find the derivative as well. So the key here is when we look at the problem, we see 8.85. Right? Now we're going to let x be that number. So in the problem, what number we see is going to be x. So now if we let x be 8.85, then substitute x in there, we have square root of x. Then we have square root of x, right? If x is equal to 8.85, and we will make that equal to f of x. So f of x is equal to f of x, x is equal to 8.85. That's nice. But what is a? Now, linear approximation, just like any approximation. Let me ask you this. If I ask you what is square root of 8.85, if you have to guess, what will be your answer? I hope that you will see that 8.85 is close to 9. So square root of 9 is 3. So the answer is about 3, a little less than 3. So that actually is not a very bad approximation, because 8.85 is very close to 9. So if we use 9, that's a very good approximation. So in the spirit of approximation, we would choose A to be close to this number, but the it will be very easy to approximate. So this problem we will choose A to be 9, simply because square root of 9 is nice and even. We can do that without the calculator. That is, we can do that without the calculator. You can just guess. Right. Now we have everything. We can put it in here. But before we do that, the function is square root of x, or x to the 1/2. At x equal to 9, f of 9 will be just square root of 9, which is 3. So we have the values of the function is 3. Now we find the values of the derivative as well. Derivative is 1/2 x to the 1/2, negative 1/2, sorry. Yeah, original power minus 1. So we have 1/2 x is 9 to the negative 1/2. Of course, sorry. Let's not do that. At x equal to 9, derivative at 9 equal to 1/2, 9 to negative 1/2. Yeah, they're not equal to. This is equal to when x equal to 9. Alright, negative 1/2 bring to the bottom. 9 to the 1/2 is the same as cube root of 9. So we have 1 over 2 times 3, or 1 over 6. Right, now we have everything ready to substitute into our problem. So A is 9, right? So this is equal to f of 9 plus derivative at 9 x minus 9. Right. Now we will substitute for x equal to 8.85 and a equal to 9. We already did that. So at x equal to 8.85, we have f of x, which is square root, which is the values we try to approximate here. Approximately equal to f of 9 is 3. Derivative 1 over 6. X 8.85 minus 9. 8.85 minus 9 is negative 0.15. Just a spirit of approximation, we will use a calculator just to get the estimate. 1 over 6 times 8.85 minus 9. If we want fraction, it is 1/19 over 40. But in spirit of approximation, we just keep in decimal. Now, so that's good. That's good and all, but how good is that? If we take the square root of 8.85, the answer is 2.9748. So it goes up to 2 decimal places. So that is very good approximation. We can almost do all of this. We can do all of this by hand. And the answer is, of course, up to 2 decimal places, almost 3. So if we round to 3 decimal places, they will be the same. So that is a very good approximation, because the point is close enough to each other. So the approximation depends on how close the approximation is. And to say, why don't we choose 8.9? That's a lot closer to 8.85, right? And of course, yes, you can choose 8.85, but the calculation is not going to be nice and even, right? So we choose a number that is close to that, but the calculation have to be nice and even, so we can get the answer quickly. So in that case, that's what we have here. Right. Go to second part of second example, sine of 2.5 degrees. So first, if we're going to graph a trig function or anything, it has to be in radian. So we can draw the tangent line, everything in radian. So 2.5 degrees, if we convert to radians, so we're going to put pi on the top and 180 degrees at the bottom. Degree and degrees cancel out. So 2.5 times pi divided by 180 is about 0. Okay, just gonna keep that 0.043633 and so on. So we approximate sine of that. Now, of course, the linear approximation, just the equation for tangent line. Right. So in this we have that number. So pretty much whatever the numbers in the equation, it's going to be x. So I will let x be that number. After that, replace x into that and this number. So we have sine x, and sine x therefore is going to be the function f of x. So now we know the function is sine x. We will choose a value that is close to this, where we can do sine of that value is convenient to evaluate. So what do we choose? Whatever we choose have to be close to this, but have to be convenient. So sine of what values is convenient? For 0, pi over 3, pi over 6, pi over 4, those are the values that we know, right? Pi over 6, what is pi over 6? That much, which is not close to 0.4 something. The one that is closest one is 0. Sine 0 is conveniently 0. So if we choose a equal to 0, we evaluate the function extremely easy. Extremely easy to evaluate. Right, so I have everything. We can just substitute in here. F of a, which is 0, derivative at 0, x minus a. Right, now the function is sine x. Now when x equal to 0, f of 0 is equal to sine of 0, which is 0. Derivative of sine is cosine. When x equal to 0, derivative of 0 is cosine of 0, which is 1. Right, we have everything. Now substitute in this equation. At x equal to 0.04363 and so on. Evaluate, put that into x. F of 0 is 0. Derivative of the function at 0 is 1. X is that number. and a is 0, then that is 0, or just x pretty much. So of course that gives us just this number. So we will have sine of this value is exactly equal to itself. So what is sine of that? Of course you see they're very close to each other. So the sine of 2.5 degree approximately equal to 0.04363. Right, so simple enough. Whatever we evaluate, whatever that number is, that will be x, and then we have the function. And then we choose a to be close to that number, but conveniently to evaluate. And when we have that, put in the equation of the tangent line or that linear approximation. So there's not much in this section. Pretty much says that. We just play with the notation. Instead of equation of tangent line, now we will replace y with L sub x, meaning that we use the line to estimate the values of the function. The second part of the section is differentials. This will estimate the change of the function if we change x. So let's look at this. We have the function. This is the graph of the function. And then here we have the tangent line. So what earlier we used the equation of tangent line to estimate the values of the function, right? Now this we will use to estimate the change in the values of y. Now originally f of a is when x equal to a, we have this point. Now we can estimate the change of the function. So let's say when a go to x, the values of the function is there. The actual change is delta y. Delta y is the actual change. When x go from a to x, that's the actual change. Now, if we use the equation of tangent line, and we estimate, this is the approximate change. So the exact values is the difference of two functions from the curve. And here we use the line to estimate the difference, and that is the approximate change. Right, so approximate change, we use the linear approximation. Right. So what's that equal to? Like I said, we just play with the notation. So approximate values of the function, if we use the line, is equal to f of a plus derivative x minus a. All I need to do is subtract f of a to the other side. Right. Now this is the approximate values using the line to get the values of the function. Now this is delta x approximately equal to delta x. I'm sorry, delta y. So approximately this is the change in the y values. Will be approximated by derivative times the change in x. So put them together. The change in y is approximated by derivative times the change in x. So let's just look at a few examples. Approximate the change in this function when x goes from 1 to 1.05. Right. So the change in y approximately equal to derivative at the point x minus a. Or we can just say it a prime of a times delta x. Let's clarify a few things. Of course, that is derivative of the function. So in this case, a is the initial point, initial values of x. Initial values, that would be confusing if I say the initial values of x. So we go from a, and it go from, so initially that a, x would be the final values, and delta x is final minus initial, which is x minus delta x minus a, pretty much. So in this case, the change, the function is that. Let's just find the derivative first. The derivative is equal to 9x to the 8 minus 2. Evaluate at a, which is 1. Derivative of 1 at 1. So it is 7. Right? Now we can get back to the formula. Estimate values for y is derivative at that point, at the initial point, times delta x. So the derivative at that point is 7. Final values 1.05 minus initial values 1. So that gives us 0.05 times 7, 0.35. Like that. Simple enough, and we can do it by hand. Now, if we actually want to find the actual values for delta y, it's very simple though. We just take the values at the final point minus the values at the initial point. So let's say it, let's store 1.05 store into x, and enter this function x to the 9 minus 2x plus 1. Now, if I put 1 into x, evaluate, same thing. So I will check the values at 1.05, which is this, minus the values when x equal to 1. For that 0, but the actual difference is 0.45. Yeah. So if you want to find the actual difference, put the final values and in the function, and the initial values in the function, subtract the two function values. Now if we want to estimate the change, if we only want to estimate the change, take derivative evaluate at the initial point and then times the change. So that's what we have. Right, now let's look at the second example. Approximate the change of the surface area of the spherical hot air balloon when the radius decreases from 4 to 3.9. So initially the value is equal to 4. So we talk about the surface area. The surface area of a sphere is 4 pi r squared. Now, or like y equal to. So the change in the area approximately equal to the derivative at the initial values times delta x. Pretty much that. Of course, initial values, it is from 4, and the final values is 3.9. The delta x, the change in the x values, or here the change in r, because r is the variable. Is final values minus initial values of x of the independent variable, negative 0.1. Right? Now if we have that is the function, derivative will be a pi times r. When r equal to the initial values, derivative as the initial values is going to be a pi times 4, which is 32 pi. Now we'll go back to our problem. The change in the surface area given by the derivative at the initial values. I just put a times delta r. It's just like this, but we replace y with a, x with r. Okay. It's still the same formula. Derivative is going to be 32 pi. Delta r is negative 0.1. So we have negative 3.2 pi. In the spirit of approximation, we'll get the values for that. Negative 3.2 pi. Negative 10.053. And the unit for this, the change in area, the unit for area is meter square for this case. Right. So the change in the y values equal to the derivative at the initial values times the change in the x. Initial values here is 4, and the change from 4 to 3.9, that's negative 0.1. And we just put everything in the formula. So that's pretty much it. Now, there's another form, like I said, we play with the notation a lot in this section. And f prime times dx, we call that the differential dy. So dy is equal to derivative times dx. The dx is the same as delta x in this case. So we just change the notation pretty much. So let f be the differentiable function on the interval that contains an x. A small change of x is denoted by differential dx. So usually we can say delta x is equal to dx because that's the change in x, small change in x. And the corresponding change f is approximated by that differential. So like I said, we play with the notation a lot. Now think about that. We can write derivative in that form, right? Move the dx over, multiply dx on both sides. dy is derivative times dx. That's exactly what we have. And that's why we use the notation like this for the derivative. Right. And then once again, dy is the differential. And the actual delta y approximately equal to that. So now we just play with the notation. Delta y approximately equal to the derivative times delta x. dy is exactly equal to the derivative. This So delta y, the approximation, delta y is the actual difference, is approximated by that. Now if we replace delta y by dy, delta x by dx, derivative at a in general, derivative with respect to x. And then we have just that. Like I said, just play with the notation. Right, now use the notation for differential to write the approximated change in this. So that should be easy. F of x equal to 3 cosine square of x. I will write cosine of x and then square. So it is easier to take derivative that way. If I take derivative, with the parentheses here, will be 3 times something square. Derivative of that is going to be 6 parentheses and derivative of the parentheses. That is the chain rule. And inside the parentheses is cosine of x. Derivative of cosine is negative sine. Put them together, we have negative 6 cosine x sine x. Let's just write the derivative. Now, we did say that the notation for derivative is dy over dx. Just need to move the dx over, and that would be it. Times dx. Now if we want to approximate the change the y, dy into delta y, and change the dx into delta x, the equal sign into approximation. Right. And then the function here, of course, I can just copy the same thing, but notice that this will be evaluated as the initial values. A is the just initial values here. Right, so that's what we have. Right, here. Use that to if x increasing from pi over 4 to that, approximate the change in the function of f of x. So here in this case, a, the initial values is pi over 4. So the approximate values of the change delta y approximately equal to negative 6 cosine of a, which is pi over 4, sine of pi over 4. I'm just going to use this formula where a is pi over 4. Now delta x is changing from this values to that values, so delta x, the change in x values, final minus initial, final minus initial pi over 4 cancel out. So delta x is 0.1, 0.01. So I have negative 6. Cosine pi over 4, that's square of 2 over 2. And sine pi over 4, same thing, 0.01. Multiply that, we have 2 over 4, negative 6, times 2 over 4, times 0.01. 6 and 4 cancel out, that 3. So I have negative 0.03. Right, so when x goes from pi over 4 to pi over 4 plus 0.01, the y values approximately will change by that much. Yeah, the y values of this function will change by that much. So if we want to estimate, so let's first pi over 4 plus 0.01. Now let's just evaluate that. Cosine of x squared, we have that values. Sorry, forgot to hit store into x. Right, now let's evaluate that at x. Alright, so that's what we have. Now pi divided by 4 store into x and evaluate this. So when x changes from pi over 4 to pi over 4 plus 0.01, the y values will change from this much, subtract this much. So that's what we have. Of course, the approximation of the change is to be close to that. It's not going to be exact, obviously. That's what approximate means, right? So that's what we have. Now, of course, like I said, we just play with the notation. The change in the y values approximately equal to derivative at the initial point times delta x. The change in y approximately equal to derivative at the initial point times delta x. Right, let's look at an application problem. By the way, in real life there will be a lot of application. Let's look at this example. An edge of a cube is measured 10 inches with possible error of 0.2 inches on an edge. So usually in real life when you construct something, there will have some form of error. And the idea here is we have to know the error for each measurement. Of course, that could be within the acceptable range. If that is the error, then what happened to the volume of an object? Let's say if you want to make a cube of gold, very important, right? If we change the measurement by that much, what happened to the volume? What is the worst possible case? So in this case, an edge of the cube, let that be x. So x is equal to 10. Maybe there's some error, plus or minus 0.2 inches. Right? So in that case, what happened to the volume? By the way, the volume of a cube, x cubed. So in that case, if we take derivative, 3x squared, derivative can be written using that notation where we move the dx over. So delta dv is equal to 3x squared dv. Now, just play with notation. If we change dv to the actual change in v will be approximately equal to delta v. This will be delta x, right? Dx will become delta x. But when we do that, the 3x squared here becomes the initial values, right? Instead of x, it have to be evaluated at the initial values. A, of course, initial values. So now ideally we want the initial to be 10, which is good. So in this case A is going to be 10, but in reality there may be some error. So the delta x in that case is the final minus the initial. Final minus the initial. 10 and 10 cancel out, so delta x is plus or minus 0.2. So what we do is we put all of that information into here. So delta v, the approximation change in volume, approximately equal to 3 times initial values is 10. Delta x will be plus or minus 2. Right, so multiply all of that. 10 squared is 100, 300. Plus or minus 300 times 0.2. So that equal to plus or minus 60. Right, so as you see, even though if the error is just 0.2 inches, but the change in volume is about plus or minus 60, the unit here will be square root, inches cubed. Because one measurement is inch, the volume will be inches, cube of inches. Right. So, of course, that is the significant of the problem. Like if you construct some form, even though if the error is very small, when we calculate the actual error of the whole object, more in this case the volume, it turned out to be a lot. Right. So of course we can use this to estimate the change. But it's a plus or minus, still plus or minus that much. Right. So in this section we only have two things. Linear approximation. So we use the equation of a line to estimate the values of the function, of course, on the curve. And then we estimate the change in y values if we change the x values. And the estimate of the change in y values is equal to the derivative at the initial point times the change in x. In this case, that's what we have. And that's all we have in this section. As always, thank you for watching and see you in another video in Calculus 1.